Hello everyone, welcome to my YouTube channel. In my first video, we have discussed the concept of relation. Okay, where we have defined three type of relation. One is reflexive. We call reflexive means we know what is the meaning of reflexive relation. Reflexive means A comma A must belongs to a relation. Number two, symmetric. What is the meaning of symmetric relation? If A comma B belongs to relation, implies B comma A also belongs to this relation. And number three is transitive. What is the meaning of transitive relation? If A comma B belongs to R, B comma C belongs to R, it always implies A comma C belongs to R. So we have defined these three type of relation in my previous video. Okay. If you did not watch this video, please go to this video to get a clear-cut concept on relation. Okay. And we know these three relation as a whole is called equivalence. This relation as a whole is called equivalence relation. Okay. And always remember here the elements A, B, C all belongs to the given set. Okay. We always have a given set, and always remember this A, B, C must belongs to this set. And after that, if these three holds, we say that it is a equivalence relation. Okay. And one more thing, relation is always a subset of a Cartesian product. In our previous video, we know how to find from our previous video, we know how to find A cross B. If okay, after finding A cross B, we can see that whether this R is a subset of A cross B. If this our relation always is a subset of A cross B. Okay. Now in today's class, we are going to define some more important concept, and after that we shall solve some very important questions from this chapter. Okay. This is everything. Okay, this is everything from our today's class. So at first we start with a very important concept. The concept is anti-symmetric relation. What is the concept? The concept is anti-symmetric relation. Okay, anti-symmetric relation. What is the meaning of anti-symmetric relation? Suppose capital A is a given set. Given set may be set of all integers, set of all natural number, whatever this is a set. And suppose R is a relation. We know relation is a subset of Cartesian product. R is a relation and capital A be a given set. Now, in that case, R is said to be anti-symmetric. R is said to be anti-symmetric if, okay, R is said to be anti-symmetric if for all A comma B belongs to the set capital A and A is in a relation with B. A, B should belongs to this capital A and A must be in a relation with B. And B also be a relation with A. A is related with B and B is related with A. Related means relation. Then you must have A is equal to B. Then you must have A is equal to B. If this condition holds, we say that it is antisymmetric. We have antisymmetric relation in my partial order set that I'm going to discuss later. Okay, that I'm going to discuss later. This antisymmetric relation is very useful in my partial order set, PO set or PO set. Okay, or PO set, whatever you called it. So A, B belongs to A. If A is related with B, B is related with A, we have to show A is equal to B. Take some examples to clear the concept. Suppose in first example, our set is set of all natural number. And in second example, our set is set of all integers. Set means integers. In means natural numbers. Natural number means 1, 2, 3, 4. Start from 1. Natural number always starts from 1. And integer means it can be negative, it can be positive. Now suppose we are given a relation. This relation is for all A, B belongs to natural number. For all A, B belongs to natural number, A divides B. Suppose for all A, B belongs to natural number, A divides B. So the question is this relation is antisymmetric? See that whether it is antisymmetric or not, it always depends on the set. Okay, always remember your set. For example, if we consider the first set, okay, start with the first set. Is this relation is antisymmetric? Suppose, suppose I am taking two natural numbers, 2 and 4. 2 divides 4, obviously 2 divides 4. But does 4 divides 2? Answer is no. 2 always divides 4, but 4 does not divide 2. That means you can't take the elements like this, because in antisymmetric relation we know that if A is related with B, B must be in a relation with A. So 2 divides 4, but 4 does not divide 2. That means you can't take the element 2 and 4 like this. Otherwise, this condition is not satisfied. So, so, so you can see that. So you can clearly see that if A divides B and if B divides B must divides A. Otherwise, this condition does not hold. Here the condition is division. So if A is relation with B, B must also be in a relation with A. So you have to take elements so that if A divides B and B also divides A, if you satisfy these two, we must take the elements like A equal to B. Otherwise, these two criteria can never be satisfied. Okay? এই দুটো ক্রাইটেরিয়া কোনোদিন স্যাটিসফাই করবে না। সি দ্যাট, ওকে, ক্রাইটেরিয়া গুলো কোনোদিন স্যাটিসফাই করবে না যতক্ষণ না আমরা A equal to B চুজ করছি। So obviously, to satisfy this criteria, we must take A equal to B, and that means it is antisymmetric. So for this set A equal to natural number, we see that this is an antisymmetric relation. For example, we can take A equal to B like 3. 3 divides 3 and 3 divides 3. Otherwise, if you take two different elements, this criteria, okay, this criteria should never be hold. Okay, this criteria will not satisfy it. So we have to take A equal to B. Otherwise, these two criteria not simultaneously hold. Because if A is in a relation with B, B also is in relation with A. Okay, so if we take A equal to 2 and B equal to 4, here 2 divides 4. So this criteria is satisfied, but 4 does not divide 2. So this criteria is not satisfied. That means you can't take the element like this. You must take the element where A is equal to B. Clear? So you see that this is an antisymmetric relation. Now for the second example, here this set is different. Set is set of all integers. So here, if we take A equal to 3 and B equal to minus 3, what happened? What happened if we take A equal to 3 and B equal to minus 3? See that. See, 3 divides minus 3, obviously, because minus 3 by 3 equal to minus 1, which is an integer. You can say that 3 divides minus 3. Also, you can see that minus 3 also divides 3. 3 divides minus 3 and minus 3 also divides 3. Okay. So these two criteria are satisfied. That means we can take the elements 3 and minus 3. We can take, because both the criteria are satisfied, because 3 divides minus 3 and minus 3 also divides 3. Right? But are A and B equal? Answer is no, because 3 cannot be equal to minus 3. 3 cannot be equal to minus 3. That means these two criteria hold, but A is not equal to B, because minus 3 is not equal to 3. That means this relation is not antisymmetric. Not antisymmetric. So it's a very important example whether relation is antisymmetric or not. Okay, like this, you can check for any given set whether it is antisymmetric or not. This division example is very, very important. Okay. So this is my last important concept from relation. It is antisymmetric. Now we shall solve some important questions which will be very, very useful for Calcutta University and any other university exams. Okay. After that, we shall define PO set, partial order set. And also, if you find any doubt or any mistake from my video, please inform me. Okay, it will be very, very helpful for me to improve myself. Okay, if you find any mistake or any doubt from my video, please comment. Okay, this is very, very helpful for me. In my next video, I shall I shall solve your doubt. Okay, I shall try to solve your doubt. So Now we shall solve some important question from this chapter. First important question. Question is, suppose Z is set of all natural numbers. That is my given set. These questions came in few exams. Okay. Suppose Z is set of all integers. And suppose we are given a relation R is equal to A comma B belongs to Z such that A minus B is divisible by 11. Suppose Z is set of all natural number and the relation is given A comma B belongs to Z such that colon means such that A minus B is divisible by 11. We have to check whether this relation is equivalence relation or not. We have to check whether this relation is equivalence or not. So how to check this? At first, we have to check reflexive property. Now, how to check reflexive property? Very, very easy. Take any element from this set. I am taking an element A belongs to Z. That means A is an integer. Now, how to prove reflexive relation? You have to prove A comma A belongs to Z. Here, this A is called domain and this A is called range. Here, domain and range are equal basically, okay? So, if you take A comma A belongs to Z, you have to prove A comma A belongs to Z. That means you have to take B equal to A. That's it. It's a shortcut method. It's a shortcut method. You have to take B equal to A. So, see that if we put B equal to A here, that will give you A minus A. That will give you A minus A. And we know that A minus A equal to 0. And we also know that 0 is divisible by 11. In fact, 0 is divisible by any number. Okay, 0 is divisible by any number. That means, yes, reflexive property holds. Therefore, we can write A comma A belongs to R. R relation. This is R. You have to show this belongs to R, not Z. A is a member of Z, then A comma A belongs to R, not Z. Okay. So yes, A comma A belongs to R. That means reflexive property holds. Now, then what? Symmetric property. Symmetric property says what? If A comma B belongs to A, if A comma B belongs to, see that, recall our symmetric property, you have to assume A comma B belongs to R. Then we have to show B comma A also belongs to R. Have to show this. Okay. Now what? How we can prove this? Now let symmetric property A comma B belongs to R. It means what? A comma B belongs to R means A minus B is divisible by 11. Always remember this A comma B comes from this set Z. You can't take any element outside Z. That means you can't take fraction because here the given set is Z. So we are given A minus B is divisible by 11. Now divisible by 11 means we can write A minus B equal to 11 into some K, where K is an integer. Why? Because divisible by 11 means it is a multiple of 11. For example, it can be 11, it can be 22, it can be 33. So divisible by 11 means it is a multiple of 11. And any multiple of 11 can be written like this, 11 into some K. What is K? Yes, K is an integer. Okay. Then we have to show B comma A belongs to R. That means interchange A and B. That means we have to take B minus A, not A minus B, because B comma A means interchange between B and A. So we have to check whether B minus A is divisible by 11 or not. Okay. What we need to check? We need to check whether B minus A is divisible by 11 or not. So B minus A, we can write B minus A equal to minus of A minus B, obviously. And A minus B equal to 11K. A minus B equal to 11K. So that become minus of 11K. Here minus sign does not matter. Okay. Here minus sign does not matter. So B minus A equal to minus of A minus B equal to minus of 11K. You can write this as 11 into minus K. And if K is an integer, minus K is also an integer. Obviously, if K is an integer, its minus is also an integer. That means what we obtain, B minus A is also a multiple of 11. It's a multiple of 11. That means B minus A is also a multiple of 11. That means, yes, B comma A belongs to R. That means it is a multiple of 11. Clear? Okay. Now the last thing we know. Now we have to check whether it is transitive or not. Transitive. Transitive. Now for transitive, we know we have to assume A comma B belongs to R and another pair B comma C belongs to R. Always remember this ABC belongs to Z. Okay, this ABC belongs to Z. Now if A comma B belongs to R, it implies A minus B is divisible by 11. If AB belongs to R means what? A minus B is divisible by 11. That means it is a multiple of 11. And B comma C belongs to R. What is the meaning of this? That means B minus C is a multiple of 11. Say that multiple is some K1. Multiple is K1. Don't forget to write K and K1 are integers. Okay. K and K1 are integers. Don't forget to write in exam K and K1 are integers. So what we are required to show? We are required to show A comma C belongs to relation. We are required to show A comma C belongs to relation. Okay, we know this concept from our previous class. So A comma C belongs to relation means what? We have to check whether A minus C is a multiple of 11 or not. A minus C is a multiple of 11 or not. So how you can check this? Say that A minus C can be written as A minus B plus B minus C. No doubt. A minus C can be written as A minus B plus B minus C. Now, what is my A minus B? It is 11 into K. What is my B minus C? It is 11 into K1. If we add them, we can take 11 common. Simple calculation. Now, you can see that K, K1, both are integers. If both are integers, their sum is also an integer. If both K and K1 are integers, their sum is integer. That means it is an integer, say it is some K2. Say K2. So that means we obtain A minus C equal to 11 into K2. That means A minus C is a multiple of 11. Multiple of 11 means, yes, A minus C is divisible by 11. That means we can say A comma C belonging to this R. So yes, this relation is transitive. So transitive is proved, transitive property. So transitive property proof means, yes, it is my equivalence relation. It is my equivalence relation. Okay, done. Anyone, any concept, any doubt from concept? Anyone, any doubt from concept? You can just write in my channel if you have any doubt on this. Now there is last concept, inverse relation. What is inverse relation? As the name suggested, inverse means just interchange between domain and range. Interchange between domain and range. For example, if A comma B belongs to a relation, then B comma A belongs to inverse relation. Its inverse relation is noted by R inverse. So inverse relation is nothing, just interchange between domain and range. A comma B, then this will be B comma A. Okay, so there is the concept of inverse relation. And recall the concept of equivalence class. We have defined we define in equivalence class in our previous video with some examples. Just go through that examples. Now the next question is based on this inverse relation. Inverse relation. Question is, consider a relation. We are given a relation question. Consider relation. Relation is given as 1, 2. These are the pair of members under the relation 1, 2, 1, 1. See that here the relation is given in the set form. In the set form 1, 2, 1, 1, 2, 1, 2, 2, 3, 3, 2, 2, 3, 3, 4, 4, 4, 5, 5, 5, 5, 4, 5, 5, 5, 4. Okay. Okay. That's it. Suppose we are given a relation like this. So question and obviously we must given a set. The set is 1, 2, 3, 4, 5. We always know relation is a member of this Cartesian product. That means the relation must be a subset of A cross A. You can check all the members in this set is a member of A cross A. We know how to find A cross A, like 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, then 2 comma 1, 2 comma 2, 2 comma 3. We know this concept from our previous video. So you can see that all these members are oh sorry, all these members in R is a member of this set A cross A. You can check all these member of this relation is a member of this A cross A, because we know relation is always a subset of A cross A. So we are given a set like this. Now what is the question? The question is, check whether it is equivalence relation. Check for equivalence relation. Number two, find R inverse. Find R inverse. Find equivalence classes. Find equivalent classes. So we are given a relation R is equal to like this, a set capital A equal to this. We have to check whether this set is equivalence or not. After that, you have to find out R inverse. Okay, that is my question. Solution. Solution. How to solve this question? At first, we have to check whether there is equivalence or not. For this, we shall show whether it is reflexive or not. How to check reflexive property? Let a member A belongs to this set capital A. That means this A can be 1, 2, 3, 4, 5. This A can be anything, either 1 or 2 or 3 or 4 or 5. We have to check whether A comma A belongs to this relation or not. We have to check whether A comma A. For example, if we take A equal to 1, see that 1 comma 1 belongs to this set. If we take A equal to 2, you have to check for every member. If we every member for every member you have to check. If we take A equal to 2, see that yes, 2 comma 2 belongs to this relation. If you take A equal to 3, yes, 3 comma 3, 4 comma 4, 5 comma 5. That means we can write A comma A belongs to R. Implies A comma A belongs to R. For example, just give an example in exam. Give an example in exam to get more marks. To get more marks. For example, 1 belongs to A and 1 comma 1 belongs to R, and so on. Explain like this. Okay, explain like this. After that, right? So the relation is reflexive. Reflexive relation. Number two, then next is symmetric. Symmetric. Whether this is symmetric or not, for this, take any two elements from this set. Okay, and let A comma B belongs to R. For example, let us take 1 and 2. 1 and 2. Obviously, 1 and 2 belongs to R. Sorry, is A. 1 and 2 belongs to A. So 1 and 2. Now, symmetric means what? B comma A must be in relation. B comma A. So here 1 comma 2 belongs to relation. See that 2 comma 1 is also in relation. That means yes, first criteria is satisfied. First criteria is satisfied. A comma B belongs to R, B comma A belongs to R. But you have to check for every pair. You have to check for every pair. Next pair, let us take the pair 4 comma 5. Yes, 5 comma 4 is also there. Okay. Next, you can take any, say 2 comma 2. Here A and B are equal. That means 2 comma 2. A and B is 2 comma 2. That means B comma A is also 2 comma 2. If A comma B is 2 comma 2, then B comma A is also 2 comma 2. And 2 comma 2 is in this set. That means you can see that for every pair, this condition hold. For A comma B belongs to R, let A comma B belongs to R. Clearly, B comma A also belongs to R. After this, you can give example to get more marks. For example, 1 comma 2 belongs to R. It implies 2 comma 1 also belongs to R. Like this, you can see that for each pair, this condition is satisfied. Okay, this condition is satisfied. So yes, it is reflexive and symmetric both. And the third point is yes, transitive. Transitive. How to check transitive property? We know let A comma B belongs to R, B comma C belongs to R. You have to check whether this A comma C belongs to R. A comma C. For this, see that 1 comma 2 belongs to R. 1 comma 2. 1, 2 and 2, 1 belongs to R. We are taking, for example, now not let us take some example. Let 1, 2 belongs to R and B, C means 2. You have to start from 2. 2, 1 belongs to R. This is my A, B, B, C. 1, 2 belongs to R, 2, 1 belongs to R. We have to check whether 1, 1 belongs to R or not. We have to check whether 1, 1 belongs to R or not. And clearly 1, 1 belongs to R. Okay. Okay. Take another pair. Taking the pair 4, 5. See that 4, 5 belongs to R and 5, 4 belongs to R. 4, 5, 5, 4. Then you have to check whether 4, 4 belongs to R. Answer is yes. 4, 4 belongs to R. See that 4, 4 belongs to R. So for every pair, now you can check yourself. For every pair, whatever be your pair, this relation always hold. A, B, B, C belongs to R. Okay, clear? I'm giving you example. This implies 1, 1 belongs to R. Yes, 1, 1 belongs to R. Just an example is sufficient, but you have to check for each and every pair. Okay, say that. If you take the pair 2, 1, say that 2, 1 belongs to R. Then 1, 2 belongs to R. That means you have to check whether 2, 2 belongs to R or not. Yes, 2, 2 belongs to R. That means whatever be my pair, this criteria is always satisfied. So how we can write this? So we have to write A, B belongs to R, B, C belongs to R. It always implies A, C belongs to R. A, C belongs to R. This means what? This means yes, transitive property hold. Transitive property hold. So reflexive, symmetric, transitive, all the properties hold. That means this relation is equivalent. This relation is equivalence. Done. Relation is equivalence. Okay. Just pause the video and write down the explanation. And now, after checking this, my second part is find out R inverse. We know how to find R inverse. R inverse is very easy to find. Just interchange between domain and range. Here, domain is 1, range is 2. So R inverse will be first element 2, 1. Here, domain and range are equal. That means 1, 1 remain as it is. Here, domain is 2, range is 1. So this will be 1, 2. Both domain range equal. Both domain range equal. Both domain range equal. Both domain range equal. Sorry, no. Here not equal. 4, 5. You have to write 5, 4. Here equal. Remain as it is. 5, 4. Not equal. So 4, 4. So R inverse is very easy to find. You can also check whether this R inverse is equivalence or not. Okay, R inverse is equivalence or not. You can check yourself. Okay, done. Finally, equivalence classes. Okay, in my previous video, I have explained how to find equivalence classes. Take another example. At first, we shall find the equivalence class of 1. Equivalence class of 1 is means what? We have to check in which element 1 is related with. Okay, we have to check to which element 1 is related with. You can see that 1 is related to 2. 1 is related to 2. That means under equivalence classes of 1 and 1 is related to 1. 1 is related to 1 and 1 is related to 2. Okay. So under equivalence class of 1, there will be 2 members 1 and 2. See that 1 is not related with 3. 1 is not related with 3 because there is no member like 1, 3. 1 is not related with 3. So 3 does not belong to equivalence class of 1. And you can easily see that equivalence class of 2 is also 1, 2. Why? Because 2 is related with 1, 2 is related with 2. 2 is related with 2. So equivalence class of 1 and 2 is 1, 2. Done? Okay. Then what is equivalence class of 3? What is equivalence class of 3? You can see that 3 is related with itself only. Selfish element. Okay, a selfish element. It is related with itself, not with any other. That is why selfish element. So equivalence class of 3 is only 3. Similarly, you can easily check equivalence class of 4 and 5 are equal. They are 4 and 5. So like this, you can find out equivalence class. Okay. So this is my equivalence class. Done. And on the basis of this, we can partition our set like. On the basis of this, we can partition our set like partitioning our set. That is, in our set, the partitioning. If we partition our set, we have the elements like 1 comma 2, then 1 comma 2, then 3. This is called partition of a set. This is a shortcut trick how to find partition of a set. Just find out equivalence classes. Just find out equivalence classes of each element. After finding this equivalence class, just write down these elements like this. This is my first space pair 1 comma 2. This is a single element 3, and there are two elements 4 and 5, and giving you a comma between them and second bracket. This is the method of writing partitioning of a set. After finding equivalence set, you can easily find this. Okay. Okay. Now, one more problem from equivalence relation. Now, this problem is very, very important question. The question is, suppose a relation R is defined as collection of all A comma B such that 3A plus 4B is divisible by 7. 3A plus 4B is divisible by 7, and the set is A equal to capital Z. Question is, show that R is equivalence. Show that R is equivalence. Okay, clear? R is equivalence or not? A solution. Solution. At first, we have to check reflexive property. Uh, First of all, we shall check reflexive property. For this, let us take an element A that belongs to Z. An element A that belongs to Z. Now, A comma A. What is the meaning of A comma A? A comma A, that means we have to put B equal to A. If we put B equal to A, we have 3A plus 4A, because A comma A means we have to put B equal to A. So if we put B equal to A, we write 3A plus 4A. 3A plus 4A equal to what? 7A. And 7A, obviously, it is divisible by 7. Because 7 into something, that means it is a multiple of 7. Okay? We have just discussed. 7 into A means it is a multiple of 7, because note that A is an integer. And remember, if A is not an integer, it is not a multiple of 7. Okay, A should be an integer. And A is an integer, obviously, because A belongs to Z. That means 7, this is divisible by 7 because it is a multiple of 7. That means we can write A comma A belongs to R. So what reflexive property hold? Now for symmetric property, it is quite difficult, quite. For this, let us take two elements A comma B. We are taking two elements A comma B belongs to R. That means 3A plus 4B is divisible by 7, and divisible by 7 means yes, it is multiple of 7. Write K is an integer. Always write K is an integer. Done. Now we have to show B comma A is in relation. What is the meaning of that? Meaning of that is interchange between A and B. Means 3B plus 4A. This 3B plus 4A is a multiple of 7. Interchange between A and B, we need to check 3B plus 4A is a multiple of 7. How we can check this? Start with 3B plus 4A. 3B plus 4A. Okay, 3B plus 4A, we start with this. Now, see that from this relation, we can find out the value of B. We can write 4B is equal to 7K minus 3A, giving you B equal to 1 by 4, 7K minus 3A. B equal to 1 by 4, 7K minus 3A. So 3 into B. Put the value of B. B is 1 by 4, 7K minus 3A. Simple calculation. And 4A remain as it is. You can also substitute A. You can substitute A as well. That doesn't matter. So This gives you 3b plus 4a. Just take the LCM. 3 7 are 21 a minus 3 to the 9a plus 16a by 4. Just taking LCM. And this gives you 21k and 16 minus 9. This gives you 7a. Sorry, plus 7a and by 4. Right? So 21k plus 7a by 4. And if we take 7 common, that means it becomes 3k plus a by 4. Right? It become uniform 7 into 3k plus a by 4. Simple calculation. See that it is a multiple of 7. It is a multiple of 7, but we have to ensure whether this is an integer or not. If this is a fraction, you can't say it is a multiple of 7. 7 is present, this is okay. Okay, 7 is present, that is okay. But you have to ensure this is an integer. In that case, this become a multiple of 7. If this is not an integer, no, it cannot be a multiple of 7. Always remember this, okay? So what is our last target? Our last target is to check whether this is an integer or not, 3k plus of a by 4. How to show this? We shall use this equation. We have 3a plus 4b is equal to 7k. We are given this 3a plus 4b equal to 7k. Now, see that we have to check whether it is a, see that when this is an integer, if this numerator is divisible by 4, you can see that if this numerator is divisible by 4, this ratio will be an integer. That means we have to check whether this numerator is divisible by 4. So, so we split 4b, 3a plus 4b equal to 7k into two parts. One part that is 4k because you have to check whether it is divisible by 4 or not. That is why 7k, I'm writing 7k like 4k plus 3k. 7k is equal to 4k plus of 3k. Okay. From this, we can get the value of 3k. Why we are splitting like this? Because we have to check whether it is divisible by 4 or not. That means we have to split 7k into two parts, 4k and 3k. So after that, we can write 3k because we need 3k. 3k is equal to 3a plus 4b minus 4k. 3k can be written like this. 3k can be written as 3a plus 4b minus 4k. But we need to find 3k plus a. So add a. Add a. So 3k plus a. If we add a, 3a plus a, that will be 4a plus 4b minus 4k. Right? 3k plus a. Done, na? Because why we are adding a? Because we have to find out 3k plus a. So 3k plus a, that become add a with this. So 3a plus a, that is your 4a, and this remain as it is. Clearly, it is a multiple of 4 because we can take 4 common. And this portion is an integer because a is an integer, b is an integer, k is an integer. So this entire portion is an integer. So we see that 3k plus a is a multiple of 4. Say this is equal to sum k1. That means we have 3k plus a is equal to multiple of 4. That means 4k1. Okay. Put the value here. Put the value here. What we are getting 3b plus 4a. 3b plus 4a is equal to 3k plus a. 3k plus a is 4 into k1 by 4. Sorry. Just a minute. 3b plus 4a, that is a 7. And this ratio 3k plus a by 4. 3k plus a, what is my 3k plus a? This is 4k1 by 4 by 4. This is my 3k plus a, 4k1 by 4, giving you 3b plus 4a. 4 gets cancelled is equal to 7k1. See that we obtain 3b plus 4a equal to 7k1. That is my target. That means 3b plus 4a is divisible by 7. 3b plus 4a is divisible by 7. That is what we are required to show. Okay. 3b plus 4a is divisible by 7. And we successfully done this. Okay, that means 3b plus 4a is divisible by 7. This gives you b comma a belongs to R. 3b plus 4a is equal to 7k1. It means what? B comma a belongs to R is in relation. That means it is a symmetric relation. Because we have assumed a comma b belongs to R, and we have proved that b comma a also belongs to R. That means yes, it is a symmetric relation. Okay, just pause the video and solve it. Okay, practice it. Just pause the video and practice. And the last one is transitive property. Transitive. What is my transitive property? Let a comma b belongs to R and b comma c belongs to R. We know a comma b belongs to R means what? 3a plus 4b is divisible by 7. Divisible by 7 means 7 into k. B comma c belongs to R. What is the meaning of that? This means 3b plus 4c is equal to 7 into some k1. 3b plus 4c is equal to 7 into k1. Clear? So, so we have to check what? We have to check a comma c belongs to R. That means we have to check 3a plus 4c is equal to some multiple of 7. A comma c belongs to R means what? 3a plus 4c is divisible by 7. Divisible by 7 means it is a multiple of 7. That means 7 into n. So how we can show this? Just add these two. Adding. Just adding. After addition, what we obtain? 3a plus 4b plus 3b plus 4c is equal to 7k plus 7k1. Okay. We add them, we are getting this. But see that we need only 3a plus 4c. So 3a plus 4c, this becomes 3a plus 4c. This becomes 7k plus 7k1. And see that 4b plus 3b giving you 7b. 4b plus 3b giving you 7b. Take it to the right hand side. So that will be minus 7. See that 3a plus 4c, this value 3a plus 4c, this value becomes 7k plus 7k1 and 4b plus 3b giving you 7b. Take it to the right hand side, that become minus 7. This means 3a plus 4c take 7 common. This becomes k plus k1 minus b. Yes, this is an integer because k integer, k1 integer, b integer. That means it is a multiple of 7. Multiple of 7, that means what? Sorry, it is 4c. Sorry, it is 4c. That means 3a plus 4c is divisible by 7. Because it is 7 into something, that means it's a multiple of 7. So 3a plus 4c is divisible by 7. That means, yes, that means a comma c belongs to R. Already written here. This is my rough work. A comma c belongs to R. That means it is transitive. So it is reflexive, symmetric, transitive, all. So it is equivalence relation. Okay, it is an equivalence relation. Done. Now, now after defining all these things, now we shall define partial order relation. Partial order relation. It is denoted by PO. PO means partial order. Partial order relation. Okay, and partially ordered set. Actually, these two are almost same. Set and relation, that is almost same thing here. Because set is the given set and relation, we know what is relation. So partially ordered relation and partially ordered set. See that, it is not a new concept. Not a new concept. We have done it. Okay. What is the meaning of partial ordered relation? This, I again repeat, it is not a new thing. We have done all these things. Okay. Suppose S be a non-empty set. Suppose S be a non-empty set. It is a non-empty set, yes. Okay. And suppose we define a relation, there is a notation of the relation. This looks like less than equal to but it's not exactly less than equal to. Okay, it's not exactly less than equal to. Just to make a distinction between them, give this like this. It's look like less than equal to. There is a relation, or it is a relation, or this sign, there is a sign symbol. Okay, you don't need to take any uh, difficult thing, or just you can write it like this. Okay, don't get confused. Whatever be the notation, forget. This notation simply implies a relation R. Relation R on the set S. Suppose our set is S is set of all natural numbers, or set is set of all integer. This is simply a relation. Forget pure set. Forget pure set. Just take his relation, some order relation. Now, when this set is called partially order, okay, then R, or here R is denoted by the symbol. That's the symbol. This symbol is said to be partially ordered relation, pure relation, if number one, if the following conditions are satisfied. Pure relation if the following conditions are satisfied. Number one, reflexive property. We know how to check reflexive. Nothing is different here. Reflexive property, but here only one change has been made, which is second property should be anti-symmetric. Anti-symmetric, and we already know how to check anti-symmetric. Okay, that is why I'm saying it is not a new thing. Number three, transitive. We know how to check transitive property. We know how to check reflexive property. Even we know how to check this anti-symmetric property. If these three conditions hold, we say that it is a partially ordered relation, PO relation, partially ordered, or partially ordered set. This set is called partially ordered set. And in notation, we write it as S, comma, this symbol. Okay, so there is nothing new in this concept. For example, if we take an example, suppose our set A is equal to example. Suppose our A is equal to Z. Okay, Z, and suppose our this relation is defined as A divides B, where AB belongs to what? Yes, yes. AB belongs to what? Yes. Whether this relation is partially ordered or not, how we can check this? We shall check this condition one by one. Okay. See that after watching this video, I hope your concept will be strong on this chapter. Okay. And after that, if you find any mistake or anything, or if you have some any doubt, or if you have any problems, doubt on any question, don't hesitate to ask me in my channel. Okay. In comment box. In comment box, you can ask anything, any doubt, or any if you find any mistake in this concept, you can also. So we shall check one by one this condition. First, if we take A belongs to this set S, here S is Z, that means A is an integer. That means A is an integer, and we know we have to prove A comma A belongs to this relation or not. A comma A belongs to this relation or not. For this, A comma A equal to what? A divides A. Obviously, A divides A, which is true. Which is true. Obviously, A divides A. That means A comma A belongs to this relation. That means reflexive property hold. Reflexive property hold. Number two, anti-symmetric property. Anti-symmetric. Now you have to check whether this condition holds or not. Anti-symmetric. For this, we have already checked this. Take A equal to 3, B equal to minus 3. Recall this example. Because both belongs to integer Z set. Both belongs to Z. Now here, 3 divide minus 3. What is the definition of antisymmetric? A comma B belongs to this, and B comma A belongs to this. It always implies A should be equal to B. At first, we are taking A comma B. Obviously, 3 divides minus 3 is 3 divides minus 3. That means A comma B belongs to this. Also, minus 3 divides 3. Minus 3 divides 3. That means B comma A also belongs to this. But can we say 3 equal to minus 3? Clearly no. That means it is not a partial order relation. Okay? It is not a partial order relation. And we say that Z comma this A divide B is not partial order set. We say that this set Z comma, it is a notation of this PO set. Okay, PO set, it is not a PO set. Okay, but if for this question you can check yourself transitive property hold. We have already checked this. You can check transitive property hold, but this anti-symmetric property does not. Okay, this anti-symmetric property does not. That means we can say that it is not it is not a partial order set. Okay, another question from this. Now you can check more and more example from any textbook. Any textbook you can check after having this concept. You can easily solve those questions. You can solve the exercise as well. And if you find any difficulty, you can ask me. Okay. Uh, Final question. Suppose suppose this less than equal to. Now they are given less than equal to. Suppose there is a relation. Given there is a relation. Given there is a relation defined on n. N means set of all natural number by a less than equal to b. A less than equal to b, IFF if and only if mod a minus b less than 1. Mod a minus b less than 1. Okay? Mod a minus b is not, sorry, mod of a minus b is less than 1. Question is, we have to check whether this set n and this relation less than equal to is pure set. We have to check whether this is a pure set or not. How to check this? We start with transitive property. Sorry, reflexive property. Sorry, reflexive. Reflexive property. Let us take A belongs to natural number. That means A is a natural number. Now, if we put B equal to A, we know how to check reflexive. Put B equal to A. Mod of A minus A, it is 0, and we know 0 is less than 1. That means here, yes, it is reflexive. It is reflexive for anti-symmetric property. See that if A less than equal to B and B less than equal to A, if we assume this two, obviously A is equal to B. Obviously A is equal to B. Because for antisymmetric, we know A must be related with B and B must be related with A. That means here A less than equal to B and B less than equal to A. In that case, if A is equal to B, obviously their difference is less than 1. Obviously, if A is equal to B, their difference is less than 1. That means, yes, we can say that it is antisymmetric. We can say that it is antisymmetric because mod of A minus B equal to 0 in that case if A equal to B and 0 is less than 1. So antisymmetric property hold. But now we have to check whether transitive property hold or not. Now you can't check the transitive property like this because see that whenever this relation hold, you must have A is less than equal to B. Okay, whenever this relation hold, you must have A is less than equal to B. So transitive property, we shall check with some example. Okay, with some example, we can check the transitive property. So if we take some value, say that A minus B, here our A minus B should be less than equal to 1 and this relation should satisfy it. Clear? This relation is satisfied for some value. So if we take some value, at first, mod of A minus B should be less than 1. So if we take A is equal to, say, 1. Suppose we are taking A equal to 1. Now see that in that case, B should be less than 1. We know our set is natural number. That is okay. See that we know our set is natural number. But But if we take two natural number a and b, we must have a is equal to b. Otherwise, you cannot take. Otherwise, their difference cannot be less than 1. For example, if you take a equal to 1, b equal to 2, mod of 1 minus 2, mod of 1 minus 2 is mod of minus 1, mod of minus 1 is plus 1, and 1 is not less than 1. Okay, 1 is not less than 1. So if this relation hold, you must have a should be equal to b. A should be equal to b. Okay, a should be equal to b. Done now? Because if a is not equal to b, and if a and b are natural numbers, again repeat, if a not equal to b and a and b are natural numbers, their difference cannot be less than 1. Their difference cannot be less than 1. So if a and b are natural numbers, and if this relation hold, you must take a equal to b. And in that case, there is a trivial relation. This is a trivial relation. Okay, there is a trivial relation. Means it will be always satisfied. It will be always satisfied. So the question arises, if 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 a less than equal to b hold, but but b is not a natural number. What happens if b is not a natural number? That means if our given set is given like, say our set is set of all real numbers, not n. Suppose our set is set of all real numbers in this question. If we take the set of all real numbers, what happens in this case? In that case, we can take a and b anything. Suppose, what happens if the set is not a natural number? Suppose I am taking a equal to a value 1, b equal to a value 1.8, 1.8. And then mod of a minus b. That means I'm taking the pair 1 and 1.8. Clearly, 1 less than 1.8, this condition hold. 1 is less than 1.8. So this belongs to this R. And see that mod of a minus b equal to mod of 1 minus 1.8. Mod of a minus b is mod of 1 minus 1.8 is equal to mod of minus 0.8 is equal to 0.8, clearly less than 1. That means 1 comma 1.8 belongs to R. Okay, 1.8. Another, take 1.8, next value. Let us take b equal to, obviously we must take b equal to 1.8 for transitive relation. For transitive, you must take b equal to 1.8 and say c equal to 2.7. C equal to 2.7. Does this two value belongs to this set? At first we have to check. See that here a less than b less than c, b less than c. This condition is hold, and see that modulus of b minus c is equal to modulus of 1.8 minus 2.7. Okay, done. Actually, what I'm doing, I'm taking two elements just like transitive relation. We know how to check transitive relation. Okay, we have to take two elements. We have to take two elements. A comma b belongs to R. Then b comma c belongs to R. This is my a comma b. Now we have to take b comma c. I'm taking b equal to this, c equal to this. What is the difference? The difference is this. This is clearly 0.9. And no, 0.9 is less than 1. So I can write 1.8 comma 2.7 belongs to R. This is my b, this is my c. So a comma b belongs to R, b comma c belongs to R. Here, done, done to. Now we have to check whether a comma c belongs to R, a comma c. Now I'm taking a equal to 1, c equal to 2.7. Clearly a less than b, clearly a less than b, but modulus of a minus c is equal to modulus of 1 minus 2.7. Clearly this is greater than 1. Clearly this is greater than 1. Okay, its value is 1.7. 1.7 to 1.7 greater than 1. So does not hold. That means transitive property does not hold. Transitive property does not hold. So what is my conclusion? My conclusion is if the set is natural number, you must take A equal to B. Otherwise, their difference cannot be less than 1. But if it's a real number, there is a possibility that their difference may be greater than 1. Okay, though these properties hold, but still, mod of A minus C greater than 1. That means what? That means A comma C does not belongs to R. There is a possibility. But if you take natural numbers, yes, in that case, this property should hold when A is equal to B. This property must hold when A is equal to B. Otherwise, mod A minus B can never be less than 1. You cannot take two elements like this. You cannot take two elements like this because if their difference is less than 1, these two elements must be equal. If this is a natural number, if this is a natural number, only in that case A should be equal to B. Only in that case their difference will be less than 1. But if it is a real number, the set is real number, their difference can be greater than 1. Okay? So this is a good example of our partial or okay order. So partial order set depends only on uh, partial order set depends on the set. And this is not a new concept. Just check as we have checked for equivalence relation. Equivalence and partial order are almost same. Okay. Now I'm giving you some homework. Okay. Just solve this homework yourself. First homework. Let a relation is defined as R is a relation. It is defined as A comma B is related to C comma D. If and only if AD equal to BC. AD is equal to BC. AB related to its CD if and only if AD is equal to BC. And our set is set of all natural numbers. Question is check whether this is equivalence relation. Check whether it is equivalence or not. Question. This is my first question. Okay, this is my first question. Is equivalence relation. Next question. Next question. Suppose we are given a set capital A is equal to ABC. Okay. ABC where they are all unequal. Here A not equal to B not equal to C. They are all unequal. They are all unequal. And suppose a relation is defined as A comma A. Relation is defined as A comma A, B comma B, C comma B, A comma A, B comma B, say C comma C, C comma C, and A comma B. This is a relation. Show that this relation is transitive and reflexive. The relation is transitive and reflexive, but not symmetric. There is an example where a relation is both reflexive and symmetric, but not both transitive and reflexive, but not symmetric. Question number three. Give an example where give a relation where it is reflexive. Give an example. You have to create an example like this. Think yourself. Give an example where a relation is reflexive and transitive. Reflexive and transitive, but not anti-symmetric. Okay. So these are some some questions that you can solve yourself quite easily. So there is everything from today's class. In my next video, I shall uh, prepare a lecture video on linearly ordered set. Linearly ordered set. It is just same like partially ordered set. There's a slight difference. In my next video, okay, I shall discuss the concept. Linearly ordered set, and number two, inequality. So subscribe to my channel if you like this video. In my next video, I shall discuss these two topics: inequality and linearly ordered set. Okay. On Tuesday, I shall upload this video in my YouTube channel. Okay, and if you require more and more video like this, you can just inform me in my YouTube channel, like complex number or any other topic. Okay, so In that case, I shall prepare video on those topics. Okay, but on Tuesday, I shall make a video on this topic, linearly ordered set and inequality. Okay, till then, bye bye.